All right. Hi, everyone. We are looking at our next unit, which is on the special segments that happen in triangles, and then also the special relationships that happen inside triangles. So let's start off with our first little section here on perpendicular bisectors. All right. So when you're looking at perpendicular bisectors, and specifically a perpendicular bisector, if you remember from a while back, is a line, segment, or ray that is intersecting another line or segment specifically at a right angle. And remember, a right angle is exactly 90 degrees. So if I come over and look at this picture, so I have my segment here, and we're going to call this segment AB. So if I'm going to create the perpendicular bisector, it has to intersect this segment. First off, bisecting means it's intersecting at the midpoint. So I need a midpoint here. And again, if that is the middle, I want to make sure I have my congruent dashes on either side of that. And let's say it's a ray that's bisecting, and it's going to do it at a right angle. So that 90 degrees right angle box should be there. And again, it doesn't matter what side of that line that 90 degrees is drawn. But again, that's what we consider a perpendicular bisector. Perpendicular because it's crossing at 90, bisector because it's hitting at the midpoint of that segment. So let's see what happens when we take that perpendicular bisector into a triangle. We have what's called the perpendicular bisector theorem. All right, so it says if a point is on the perpendicular bisector of a segment, then it is equidistant which means equal in distance from the endpoints of the segment. So if I'm looking specifically at this picture, all right, so line CD is the perpendicular bisector of my segment. So again, there's my congruent dashes there. So A to D is exactly the same as B to D. I have my 90-degree box there telling me that it is perpendicular. And so specifically what that theorem says, no matter what point I look at on this line that is the perpendicular bisector, it is equidistant to those endpoints. So A to C is exactly the same length as B to C. My second point down, same thing to those endpoints. It is exactly the same distance. And I could keep going with my next point. The third one down is equidistant. And notice I'm having to go up in my dashes each time. And same thing with the point below. It is equidistant to those endpoints. All right. So no matter where that point is drawn on that perpendicular bisector, it is always equidistant to the ends. It's the same distance away because again, that line is sitting in exactly the middle of that segment. So it's always going to be the same distance out to the ends. And so that's what that theorem is saying. So now let's see how we can use the perpendicular bisector and the perpendicular bisector theorem to answer some questions. So example 1 here, find each measure. So we're looking for A to B. That's the side I'm looking for. Okay, so if AC is my perpendicular bisector, again, how do I know line AC is? Well, it's hitting the midpoint C because of those congruent dashes. It's got the right angle going on, so that's my perpendicular. And so if A to B is one stretch, oops, sorry, wrong color, then I need to look on the other side because it's using that perpendicular bisector theorem. So that means 4.1 is also on the other side. So A to B is also 4.1 units. Let's check out example 2. This time we're looking for Y to Z. No, I'm sorry, W to Y. So I'm looking for that. So again, I want to see where is my perpendicular bisector, and that is line YX. So those two pieces need to be exactly the same. So I can copy the 3 over. So WY is equal to 3 units as well. Well, what if I needed the whole way across? We don't specifically need it for this question, but we're going to go ahead and do it. So let's say we needed WZ. All right, WZ is all the way across. Well, remember, if 1/2 is 3, so is the other, which means both pieces just need to be added together. So again, we've seen if we only need half and then if we need the whole way. So let's see what happens now when we bring in some algebra. All right, so again, we have a perpendicular bisector. Again, I know line SR is my perpendicular bisector because again, S is the middle because of the dashes. At point S, you have a right angle. So again, perpendicular for the right angle, bisector for the congruent midpoint. So that means those two side lengths are equal. So I can use that to solve. So this goes back to part 1 is equal to part 2. So 2x plus 3 is equal to 4x minus 7. And now we can solve this. So I'm going to subtract my 2x to both sides. So 3 is equal to 2x minus 7. Now we can add the 7 back. So 10 is equal to 2x. Divide both sides by your 2. And my x is equal to 5. 10 divided by 2 means it's 5. Now, specifically, the question says, find the length of RT. Again, we're looking for RT here, which is the 4x minus 7. So now that I know x is 5, we're going to plug it back in. So 4 times 5, because we just said x was 5, minus 7. So 4 times 5 is 20. Take away 7 for 13. So RT, 13 units. All right, so let's see what happens when we bring in some other parts of your perpendicular bisectors. Now, every triangle has 3 sides. So when we bring in your perpendicular bisectors specifically to these triangles, we're going to get what's called concurrent lines. So specifically, what are concurrent lines? Well, these are 2 or more lines intersecting at the same point, and we call that point the point of concurrency. It is specifically called your point of concurrency. Over our next couple of sections, we're going to be looking at different kinds of points of concurrency that you're going to get inside triangles. Just today, we're starting with the point of concurrency of your perpendicular bisectors. So let's see what happens when we deal with your perpendicular bisectors in a triangle. So specifically, they're going to be drawn from midpoints. So remember, we're going to look for those congruent dashes. So on the triangle over here, let's go ahead and put in our midpoints. So each triangle is going to have 3 midpoints, 1 for each side. So now because these are my midpoints, I'm going to give them dashes on each side. Notice I'm using a different number each time to show that each side is different. All right, so now we've got our midpoint. So that takes care of the bisect part. Now we need the perpendicular part. So from each of these dots, I need a perpendicular 90-degree line. So I'm going to do my best here and draw 90 degrees. Oops, I think my middle dot got a little off. Sorry, let me start that over. Now, it's perfectly fine if your perpendicular bisectors are not hitting vertices here. Now, all three of these lines, these perpendicular bisectors, do in fact intersect at the same point. And remember, I'm drawing this by hand. I'm not using a ruler or a compass and protractor. So it is going to look a little bit off. But again, all three of these intersect at the same point. Sometimes this point can be outside of the triangle. Sometimes it could be inside of the triangle. Sometimes it could be exactly on a line or on the side of it. But this specific point is called your circumcenter. Where all three of those perpendicular bisectors come together. So specifically, what is the circumcenter? Well, for us, the circumcenter of your triangle is the point of concurrency for your perpendicular bisectors. Now, it's got some special things involved here when we do look at the circumcenter of triangles. So we get the circumcenter theorem. And this says the perpendicular bisectors of a triangle intersect at one point called the circumcenter. And it is equidistant or equal in distance to the vertices of the triangle. So if I take that same picture, my circumcenter was outside of the triangle. And again, that just so happened to work in this one. But again, the theorem says that that circumcenter is the same distance to all three vertices. Okay, that dot is the exact same distance to all three corners of your triangle, regardless of where it is. If it's inside the triangle or outside the triangle, or maybe just on an edge, it's always going to be equidistant to those corners. So I'm going to draw another triangle off to the side, one that's not quite as obtuse. Oops, let me see if I can get a better triangle here. There we go. And if we do the same idea, so there's one perpendicular bisector. There's my second one. And there's my third one. This time, it's sitting inside the triangle. So you can see with an obtuse triangle, it's outside, an acute triangle, it's inside. If we had a right angle, it would be on the edge. But no matter which direction we look, this circumcenter is exactly the same distance to all three corners of the triangle. All right, it's exactly the same length all the way to the corners from wherever that dot is located. And that's another way to see the theorem. All right, so example 4, point P is the circumcenter of triangle ABC. List any segments congruent to each segment below. So let's see what we've got. Now remember, all of these dots that are on the edges where the right angle is, those are midpoints. So on either side of R, those sides match. Either side of S, those pieces match. And either side of T, those match. And if P is my circumcenter, then remember, P to all three corners match. So let's use this now that we've kind of color-coded it with all our matching pieces to find our congruent parts here. All right, so B to R, segment BR. Is that piece? Well, it's got to be congruent to AR, the other side. All right, now let's see where CS is. C to S is using the midpoint, so then it's congruent to AS. And now let's do the last one. BP, segment BP, goes from a corner to the midpoint. So it's congruent to two other pieces. Corner to midpoint, so A to P, segment AP. And congruent to CP. So it's all about knowing where are the congruent pieces here that we need. All right, guys, I hope you enjoyed learning a little bit about your special segments. Tune in next time when we look at specifically the angle bisectors and a different point of concurrency. Bye, guys.